So relationships involving heat of reaction, change in enthalpy. The change in enthalpy is written for a particular chemical equation because it depends on the amount of stuff, and so we're writing it to depend on the moles of stuff in the equation. So if the equation or the reaction changes, delta H is also going to change. So if we multiply the chemical equation by some factor, then delta H is also going to be multiplied. So the example here is I've got A plus 2B is forming C, and it gives off a certain amount of energy. Well, if I double the size of this reaction, am I going to get the same amount of energy? Per mole I am, but total, I'm going to get twice as much energy. If I burn twice as much gasoline, I get twice as much heat, right? So if I multiply the equation coefficients by some number, then I have to multiply delta H as well. If I reverse the chemical equation, then I change the sign of delta H. So A plus 2B going to C is this delta H. If I go backwards, whatever that released, it would have to absorb because conservation of energy. Otherwise, we could make a reaction go forward and backwards and have energy get produced, and we can't. It's like buying and selling. So if this one, I'm selling it to you, so you're giving me money. The reverse is I'm buying it from you and I'm giving you the money back. It's just a back and forth. So you reverse, you turn it around, you change the sign. And then Hess's law, which is also about part of what we're doing in lab today. Hess's law is based on the idea that the change in enthalpy is a state function. It doesn't depend on how you got there. So we can find the change in enthalpy for a reaction by looking at changes in enthalpy for reactions that add up to the desired reaction, even if that's not how we do the reaction. So if I'm starting here, and I do a reaction that where our delta H is positive, and then another one where delta H is negative. The sum of those two chemical reactions, here's A plus 2B going to C, that's this one, A plus 2B going to C, and this is C going to 2D, C going to 2D. When I add those two equations together, the C's cancel out, right? Because the C was made and the C was destroyed. And so this is the overall reaction. Its enthalpy change is the sum of those two. The reason this is really cool is because there are some things that it's difficult or almost impossible to actually measure. But if you can find a series of chemical equations, chemical reactions that can be measured, or even better yet, someone else has measured and you can just look up in the CRC, then you can just add them together and you don't actually have to do an experiment. So this is how we can measure or determine delta H for a reaction that might be difficult or impossible to measure. So what we're going to do is we're going to take reactions where the delta H's are known, and we're going to manipulate them in a way so that they add up together to give us the desired equation. And we add up the delta H's. Okay. Here we've got 2A plus B going to C, and delta H is 122. The question is asking us for delta H for this. So we have to ask ourselves, how is this equation different from that one? It's reversed, right? Here we've got A and B going to C. Here we have C going to A and B. So what's that going to do to delta H? It's going to change the sign, right? So reversing the reaction, now we've got minus 122 joules. What's the other thing that's different? The coefficients, right? Here the coefficient on C is 1, and here it's 2. Here A is 2, and here it's 4. B is 1, and here it's 2. It was all multiplied by 2. I've got twice as much stuff reacting, and so I've got twice as much energy change. So what's the answer? Minus 244. Letter D. Any questions? If I buy twice as much stuff, does the cost stay the same? No, the cost doubles. If I sell it instead of buying, do I still give you money? No, you give me money. So it's still just like money, right? You got more stuff, more money. Less stuff, less money. More reactants, more energy. Less reactants, less energy. Yes, I multiplied the delta H by 2 because this equation, this chemical reaction, was this one multiplied by 2. So the first thing we observed is that the reaction was backwards. So reversing the reaction would be C going to 2A plus B. And so that made me change the sign because it's buying versus selling, switching direction. And then I'm looking at this and saying, well, this doesn't match up exactly with that. This is multiplied by 2, right? We got 2 times the whole thing. So we got 2C going to 4A plus 2B. Twice as much stuff reacting, so twice as much energy change. Okay? Any other questions? You're going to love this. Okay, find delta H for this reaction and use these reactions with known delta H's. So if you like logic puzzles and things like that, you're going to like this, and most of you aren't going to like this. It's okay, it's not a huge deal. Just try to follow along. So what I'm going to try to do here is combine these 3 chemical equations so that they're going to add up to this one. And this is a little brain twisting, but at least I'm given 3 equations. I have to use them all, and I don't have to go look up anything else. You go look up these equations in the CRC, and there's thousands of them, and you have to pick the ones that you need, and so there's a lot more possibilities. So how do you even start this? Well, what I'm going to do is I'm going to try to get things on the right side. So here I have a reactant that's N2O. So I'm going to look at these things and see which one has N2O in it. Oh, this one does. So the things I can do to these equations, I can reverse them, switch the reactants and products, or I can multiply them by numbers. So here, the NO2 is on the reactant side, N2O is on the reactant side, and so that one's the correct direction. So I'm going to write that down. 2N2O going to 2N2 plus O2. Now, did I mess with the equation at all? No, I just copied it down. So the delta H for that is unchanged. It's still minus 163.2 kilojoules. So I've got N2O on the correct side. And I want NO2 on the reactant side as well. So I'm going to look for NO2. This one has NO2, but it's on the product side. So I need to reverse this. I'm going to write this one backwards. So I'm going to put the reactants on the product side and the products on the reactant side. And so that's going to be 2NO2 going to 2NO plus O2. I just took this one and wrote it backwards. So if I reverse the reaction, what do I do to delta H? I change the sign. So delta H is then positive 113. Okay, so far? And then I want NO on the product side. I've got NO on the product side, but I've also got N2 and O2, and I need those to just not be anywhere, right? And I can't just like subtract them. But here I've got this equation that's got N2 and O2 on one side and NO on the other side. And so if I put this one in here with nitrogen and oxygen as reactants, and then I have nitrogen and oxygen as products, I can get them to cancel out when I add these together. So N2 plus O2 making 2NO. I didn't do anything. I just copied it down, so its delta H is unchanged. And so that's plus 182.6. You didn't have to put the plus sign, but we're just kind of emphasizing, yes, I considered the sign, I decided it was positive. So then let's look at this and see if this is going to work out. So I want the nitrogens and the oxygens to cancel out. I've got 2 nitrogens over here, and I have 1 down here. I need 2 of them to cancel out. I have 2 oxygens over here. I have 1 oxygen down here. So I need to multiply the equation by 2. So 2N2, 2O2 to 4NO. And then if I multiply the equation, I have to multiply delta H. Because twice as much stuff is reacting, so twice as much energy is changing. Now the N2 on the left and the N2 on the right cancel out. And here I have 2 oxygens and 2 oxygens, and those cancel out. I'm not seeing anything else that cancels out, so I'm going to write stuff down here. Got 2N2O plus 2NO2 making, I've got NO all over the place here. So 2 no's and 4 no's make 6 no's. And for that equation, we would add these things together. Minus 163.2 plus 113.1 plus 182.6 times 2. So delta H for this reaction is positive 315.1 kilojoules. Is this the same as that reaction? It's really close, it's just doubled, right? So to turn this equation into that equation, I need to divide everything by 2. So if I'm dividing all of these by 2, I'm going to divide delta H by 2. Because what I'm describing is half as much stuff as this, right? So I take that 315, I divide by 2, 157.55. So delta H reaction equals 157.55 kilojoules. With sig figs, we'd call that 157.6 kilojoules. Any questions? What we're going to do in lab today is we are going to look at 2 reactions, and we're going to measure this one and calculate its delta H, not this specific one, but we're going to measure the first one, calculate its delta H. We're going to measure the second one and calculate its delta H. Then we're also going to measure the complete reaction happening at one time and measure that delta H. And so then we can demonstrate whether Hess's law is correct or not within our, inexperienced hands, because the sum of the 2 parts is supposed to equal the total thing. 157.6. More practice. I'm not going to do that one right now.